Today, I'm going to introduce our research project TextShield. And this work is collaborated with Tianyu, Professor Shouling, Rong, Zhang, Quan, Mingyang, and Ting, Wang. Recent years, deep learning-based techniques has achieved great success in many tasks, even include security-sensitive tasks, such as toxic content detection. Due to its impressive performance, many companies have developed automated toxic content detection systems to replace time-consuming and laborious manual censorship for covering the diffusion of toxic content on their platforms. However, it is reported that many deployed systems are now suffering from the vulnerability to adversarial tasks manually crafted by real-world malicious users. And this phenomenon is very common on Chinese online social media. For example, to make insulting comments invasive, malicious users may obfuscate some toxic words to its variant, and these variants are visually similar to their original word but are able to effectively evade the detection. However, there still has no effective defense methods can be applied to handle this obfuscated toxic content, while manually reviewing these tags is usually time-consuming and laborious. In the past few years, plenty of attacks have been proposed for generating adversarial tags. However, only two kinds of defense have been explored to enhance the robustness of English NLP models, and the effort of improving the robustness of Chinese-based NLP models is still fairly limited. Even worse, the unique property of Chinese make Chinese-based adversarial attacks more powerful. For example, Chinese tags are composed of a set of characters that are individually meaningful, and the modification of a single word may damage its semantics, making Chinese-based models more vulnerable. Unlike the alphabetical language like English and French, Chinese has a large character space in which each character may be perturbed by various strategies such as phonetic-based and glyph-based strategies, making the perturbations more sparse. Besides, most of Chinese adversarial tags are manually crafted by real-world malicious users, which are more diverse. Due to the sparseness, diversity, and dynamicity of Chinese perturbation, existing defense proposed for English-based NLP models can hardly be extended to the Chinese domain. Given the above challenges, we propose TextShield, a defense framework designed for Chinese-based classification models, and the whole defense framework can be formally defined like this. Given an adversarial text generated by an attacker who have query access to the classification model, we aim to defend such attack by using neural machine translation to restore this adversarial text and then universally improving the robustness of the classification model by multimodal embedding. This is the framework of TextShield. First, each input is translated by an adversarial translation model for denoising some of the perturbations. Second, the translated text is converted to multimodal embedding, which extracts its semantic glyph and phonetic features for dealing with the corresponding glyph-based and phonetic-based perturbations. Then, the extracted features are fused to form a semantic-rich representation for the regular classification. Our translation model is designed based on the encoder-decoder framework. In the training phase, we first construct a large adversarial dataset by generating a plenty of adversarial and benign sentence pairs through attacks. Then, the designed model is trained on this dataset to learn the process of reconstruction from adversarial text to its benign counterpart. Once training is completed, the translation model is then used as an adversarial text corrector to reconstruct the input. The second stage is multimodal embedding, which aims to extract the semantic, phonetic, and glyph features of the input for defending against the corresponding perturbations. The first modality is semantic embedding, and we use the word-to-vector scheme to learn embedding vectors for capturing its semantics. The second modality is phonetic embedding, which aims to extract phonetic features of each character for capturing the similarity between the perturbed word and its benign counterpart, which have the same pronunciation. For phonetic embedding, we first convert each character into its pinyin form and then use word-to-vec to non-embed vectors over the pinyin form. Finally, we designed a glyph embedding model to extract the glyph features of each character for the same purpose. Then, the embedding vectors learned from different modality are fused to form a semantic-rich representation. In our paper, we experiment with two different fusion schemes that are early multimodal fusion and intermediate multimodal fusion. Finally, the fused features will be fed into a classification model for regular classification. We evaluate TextShield on two real-world tasks. In our defense framework, we implemented a TextNM and a BiSTM as the different backbone classification models, and we leveraged TextBugger as the attack method and compared TextShield with two spelling check-based methods and 4 industry-leading TOTS content detection platforms. And we applied 8 evaluation metrics to quantify the performance of TextShield and the compared methods. We first evaluated the efficacy of TextShield under the non-adversarial setting to verify whether the applying defense will have negative impact on the model performance. From table 2, we can see that TextShield has little impact on model performance over benign text and outperforms the baselines. As illustrated in Figure 4 and Table 3, the training loss of the translation model converged quickly within about 20,000 steps and achieved impressive performance over all metrics. This indicates that it is feasible and easy to apply neural machine translation to restore adversarial perturbations. Then we evaluate the effectiveness of TextShield in the real-world adversarial scenario. Table 4 and Figure 5 shows the evaluation results on the user-generated obfuscated text connected from real-world Chinese online social media. And we can see that the models shared by TextShield achieved considerable high accuracy with high confidence over the obfuscated text, and the combined defense scheme is more effective and significantly outperforms the baselines. So far, we have only considered static adversaries, and in this evaluation, we consider the challenges TextShield may face when adversaries know our defense. Under this adaptive setting, the classification model and TextShield will be viewed as a whole pipeline by attacker when exploring model sensitivity. Table 7 shows the attack performance against all target models, and we can see that adaptive attack has achieved considerable high success rate against the common models and the models defended by spelling check-based methods. In comparison, it has only achieved a no success rate below about 30% against models defended by TextShield. This indicates that TextShield can significantly reduce the attack success rate and is more robust than the baselines. We also investigated the sensitivity of the target models against each bug replacement. The sensitivity score represents the reduction in TOTS confidence output by the target model for each bug replacement. From Figure 9, we can see that the sensitivity of the target model defended by TextShield are markedly smaller than those of the common models across all cases, and both multimodal embedding and adversarial translation can significantly reduce the model sensitivity against bug replacement. Besides, we made a comparison with 4 industry-leading Chinese TOTS content detection platforms who have claimed to be successful in handling variant texts. From Table 9, we can see that these platforms are still vulnerable to adversarial attack. In comparison, TextShield is more practical and superior in decreasing the attack success rate, and we are currently in the process of integrating TextShield into Alibaba GreenNet to enhance its robustness. Finally, we started extending TextShield to English-based NLP models to examine its generalizability across languages. This experiment is conducted on the classical sentiment analysis task under the same adaptive setting, and the main result is shown in Table 10, from which we can see that TextShield shows good generalizability across languages and can be extended to some other languages. In conclusion, we made the following contributions in our work. We proposed TextShield, a defense framework specifically designed for Chinese-based classification models, and the experimental results showed that it is effective, robust, and generic. Then we compared TextShield with 4 industry-leading platforms, which shows its practicability and superiority. Finally, we extended TextShield to English-based NLP models, which shows its good generalizability across languages. That's all. Thanks.